All right, I'm going to work through these sheets that we had received in class on how do we break up these forces into components. So again, the question is the very practical idea that not all forces are in the X and Y directions, that you do usually have forces that are at angles. So this might be an example of somebody pulling something across the floor with a rope that is actually at an angle. Imagine somebody sliding a suitcase or something like that. They're pulling on with a strap. There would be friction opposing the motion that is parallel to the floor. There would be a normal force, a weight, and so on. So we don't even want to worry about numbers. So don't worry too much about getting the numbers. What we're trying to do here is make this picture become one that can only have X and Y components to it, or that would only have X and Y components to it. So as we take a look at this, we recognize that any force that is at an angle can be broken up into components. So if we go back to our math and think about SOHCAHTOA and a right triangle. Sorry, I thought I paused. So we're going to go back to my whiteboard. All right, so let's go back to just a regular triangle, right? So in math class, you learned that if you have a right triangle, right angle here, you call this the hypotenuse side. If this is the angle that you know, theta, the adjacent side, the side touching that angle, is known as the adjacent. If you look across the angle, that's called your opposite side. So SOHCAHTOA relates all the sides and angles together. When you saw SOHCAHTOA, you would say the sine of the angle theta is equal to the opposite side divided by the hypotenuse. The cosine of an angle theta is equal to the adjacent side divided by the hypotenuse. And the tangent of an angle theta is equal to adjacent divided by hypotenuse. So if we take a look at that triangle, that's in your math class. That's a tool that you learned in your math class. The practical application of that is we have the same thing here with this force. We have a force that's at an angle, some angle theta, right? And that force is an applied force. So we can look at that force as, instead of an angled force, we can look at it as having an X component, something pushing it to the right, and a Y component, something pushing it up. I have to switch colors there on you. Okay, so we need to label those. I'm going to call this side the force applied X component. This side is going to be the force applied Y component. So I need to follow the same rules that I have up here to figure out what are these two sides. So if I write down the sine of the angle theta is going to be my opposite divided by hypotenuse. So for my picture, the sine of the angle theta is my opposite side, which is F applied Y all over by F applied, the hypotenuse. The cosine of the angle theta is equal to the adjacent side, force applied in the X, divided by force applied. Whoops, go back to adjacent divided by hypotenuse, just to be consistent. So applying that to my picture, cosine of theta is force applied in the X divided by my hypotenuse. The tangent of theta is equal to the opposite divided by adjacent. So if I needed it, we'll find we don't really need that, is force applied in the y divided by force applied in the x. So if my question, what we really want to do is say, I can use this force, or I can look at that as being the sum of this force plus the vertical force. When I add those two together, I get this. And I use the analogy to say, in class, if I had the number 10, you could say that's equal to 6 plus 4, right? Here in vector math, when we're dealing with vectors, I can add these two vectors together to give me this vector. Mathematically, I'm either using 6 plus 4 or 10. Because they're equivalent to each other, I can put either one in my problem. In vector math, I can either use the x and y components, or I can use this one. I get to choose because they're equal to each other. So if I go back to this picture, I don't know how to do the math. It does not fit Newton's laws, right? So if I take a Newton's laws and I have x and y components, that does not fit my x and y component, and I do not want to put another direction to this. It just makes it very, very messy. So instead of using the force applied at 30 degrees, I would rather look at this as having an x component, right? And also a y component instead of the force applied. So if I go back and I label those, this would be force applied in the x, and this is force applied in the y. I cannot use all three of them at the same time. Just like if I go back to my math, I can't use 10 and 6 plus 4. I use one or the other because they are equal. I use in a problem one or the other because they are equal. So if I go back to my picture, right, in my problem, when I redraw this, what I really want to say is, okay, if I draw my original picture and keep everything that was in the x and y, so I'm going to keep my normal force, I'm going to keep my force of friction, and I'm going to keep my weight. But now I want to, instead of using my force applied, I want to use force applied in the x, and I want to use the force applied in the y. Remember, when you draw your free body diagrams, everything originates from the object. So my question is, what are these components, right? What is the x and y components? So if I look at this, because I know this angle theta here, I would use the cosine function for the x because it's the adjacent side. So in the x direction, and I suggest you write it out in long form and say that the cosine of the angle theta is equal to the adjacent divided by the hypotenuse. So force applied, cosine theta, is equal to force applied in the x. In the y direction, it's the opposite side. So in the y direction, I want to say that the sine of the angle theta is force applied in the y divided by force applied. So force applied sine theta equals force applied in the y. So now I have two equations, right, that allow me to figure out what these two components are based on their angle and the original force. Not worried about numbers. I now just have those in equation form. Back to my summation equations. Now I can write my summation equations to say, okay, all my forces in the x, again, taking anything to the right positive, anything to the left negative, up positive, down negative. I would say I have a force applied in the x plus negative the force of friction equals MAX. So I would say force applied in the X minus force of friction equals MAX. In the Y direction, when I look at it, we are going to have the normal force plus force applied in the Y plus negative W equals MAY. Rewriting that, just put a little division here. Force normal plus force applied Y minus W equals MAY. Same thing we've been doing. I just now have these extra forces because of the components that make up the force applied. Again, no different than mathematically. If I would go back and put in an equation, let's say I have an equation of 25 plus 30 plus 10 plus 2 equals something, right? Instead of the 10, I can say it's 25 plus 30 plus 6 plus 4 plus 2. And certainly, you can replace all of those with something else. And honestly, in any of these pictures, I can replace these vectors with something else. When it comes to triangles, the right triangle is the only thing that the SOHCAHTOA works for. And it allows us to keep everything in the X and Y directions. So in this problem, whoops. Okay, it got a little bit more complicated because we broke up both of these forces. So we can do that way. I'm going to quickly do this. So then you can go back and check your work. This would have an X component. I'm going to call that force thrust in the X. This would have a Y component, force thrust in the Y. We could come over here and give this an X and Y component as well. To go from here to here, I would walk across to the left and then go down. So this would be your force of the air in the X, and this would be force air in the Y. So remember, we don't want to keep the original forces. So I want to get rid of these and get rid of that and only look at those components. So when I go to do my redrawing these over again, if I come down here, my new free body diagram is going to be force thrust in the Y. Got that one. Force thrust in the X. Got that one. W. Got that one. Force applied in the X, or force of the air in the X. Got that one. And then force of air in the Y, pushing down. Got that one. So now I have a new free body diagram in which I have included all of these forces. So the trick, you're going to do your SOHCAHTOA to find each of the components up here. So if we go back and we want to do our SOHCAHTOA, again, the cosine goes with the X. So this would end up being force thrust cosine theta equals force thrust X. Force thrust sine theta equals force thrust in the Y. In the X, I'm doing a little quicker, sorry, but in the X, in this case, if I want to look at the air resistance one, I can again say the cosine function adjacent force air X divided by hypotenuse force air. So force air cosine theta equals force air X. And then you have the sine theta equals force air Y all over force air. So force air sine theta equals force air Y. So those give me equations I can use down here, right? Can use both of those. But as far as making these equations fit my free body diagram, nothing has changed. I need everything in the X and Y. Anything going to the right is positive, to the left negative, up positive, down negative. So it's essential, again, this is the most important part, to make sure you get that the picture, the free body diagram, correct. So here it's going to be force thrust X minus force applied, or from the air, X, equals MAX. In the Y, we have force thrust Y going up, but the other two are going down. Force of the air Y minus W equals MAY. And those are all of our forces. Well, hopefully that helped. Your homework was to set up. I want you to do this part, break up the components, and then draw your final picture, final free body diagram, like this, with the final equation. So I want the same thing we're doing on this sheet for problems 2, 4, and 8 set up. So no numbers involved. We're just setting up the problem. Good luck. I hope this helped.